Hello Stats class, this is 3-2C notes on a little more about residuals and measuring fit. Specifically, I want to remind you that a residual is the vertical distance. This is a review from 3-2B. Above or below the line. Above would be a positive, and below would be a negative, and it's found by doing the actual value minus the predicted value. You can remember which is which by thinking AP. So y minus y hat. Oops, not y bar, y hat. So that is what a residual is. We're going to do a few more things with residuals today and how you can use them to measure the strength of your fit. So let's talk about a regular scatter plot versus a residual plot. And we'll draw some more pictures today. So once again, I'm going to have you draw just a positive trend. It does not have to be quite exactly the same as mine, but I'll remind you that if you have the line of fit drawn, then here's a negative residual, for instance, and here's a positive residual. And the residuals show the overall pattern of the graph. I'm going to make these points a little darker so they're easier to see. And then I'm going to make that into a residual plot. And yours might look different than mine, but I'm going to try to make it as much like this as possible. So a residual plot, instead of having y on the y-axis, it has the residuals on the y-axis. And that means 0 is in the middle. This is still x, or some books do y in that spot. It actually doesn't matter, and I'll tell you why in a minute. But this one's a little bit above the line, and then a little bit below the line, and then this one's a little bit above and a little bit below. I'm trying to match what I did over here, and above and just barely below, and another one that's above. So try to make yours match. And this particular plot is what it looks like if your line of fit is good. It is randomly scattered above and below the line. I don't see any curve going on here. I don't see any slope pattern. It's just random points above and below the line. And what it does is it makes it easier to see that you've gotten the pattern right. So this is a good fit, this graph I just drew. And the reason it's a good fit is it's randomly scattered with no pattern, no curve, no anything, just it's random. And then here's an example of one that's not so good. So let's draw another one. This time do a curved plot. So I'm not making a huge curve, I'm making it slightly curved, which is kind of a little hard to tell when you just are looking at the graph at the first glance. When you look at something like this on a residual plot, it will be more obvious that it's curved. And so these points are not quite as well matched up as the other ones. But the idea is, if you draw the line, you can see some points above the line and then some points below and then some more points above. That's the curve that I'm talking about. Same thing over here. You can see some points above at the ends. You can see some points below in the middle. That is not supposed to happen. This is how you can, this is one way to tell that the line is not a good fit. And basically this isn't a linear graph, it's a curved graph. So you can see the curve more clearly on a residual plot. The pattern, which is the curve, is not explained by the line. Or in other words, the line does not tell the whole story. And we'll talk actually next week when we do a little bit of chapter 12, we'll talk about what to do about that curve thing and how to fix that. But right now we're just going to recognize that, oh gee, it's not linear because it's curved. And you can see the curve, like I said, more clearly on a residual plot than you can on an original plot. It just basically flattens out this line so that all you're looking at is above and below the line and that pattern. So that's a residual plot. This one's good and this one's bad. And just so you have some examples of that. Ideally, we want our residuals to have two properties. We want them to be relatively small compared to our data. Specifically compared to, remember domain and range? We were comparing it to the range of the data. If we're talking about Y values that are spread out a certain amount, we want the residuals to be a lot less spread out than that. So we want the values of the residuals to be pretty small compared to our spread of Y values. And then we also want our residuals to be randomly scattered with no pattern. And that's a sign that the data is linear. So the randomly scattered thing, you're mostly going to tell by looking at the residual plot. The relatively small thing, there's a couple of ways of measuring that. And so the two ways that we're going to measure it is, first of all, you can find the standard deviation of the residuals. Most of the time, when you're looking at computer output, it'll give you that. I'll show you how to do it on the calculator later, but for this first assignment, they're just going to give you that value. But we're talking about how far off those predictions are on average. Or you could also call it a typical prediction error. And the formula is a little bit fancier than the usual standard deviation formula. It's still called S, but I'll go ahead and give you the formula, but I'm going to tell you that you're usually not going to use this formula. It's the sum of all the y's minus y hats. Those are the residuals. You square them, you add them together, you divide by, this time it's n minus 2 instead of n minus 1. The reason why is long and complicated, but I'll tell you that that is called the degrees of freedom. The short reason why it's n minus 2 is we have two variables now. And I'm not going to give you the long reason right now. We're going to see a lot of different degrees of freedom for different situations in this later on in this class. So just get used to that changing sometimes, and just you're going to write down what it is in this situation and then do that. I'm not going to spend a lot of time explaining the complicated. It's kind of graduate school level math that goes into why this has to be n minus 2. You don't need to hear that. But basically, this measures the strength of how well the line fits because it tells you how far off your predictions are. So it's a measure of strength in terms of the scale and units of the data, unlike correlation, which is not based on units. So it measures how well the line fits. Strength is about how well the line fits. Smaller is better. It has to do with that we want our residuals to be relatively small. This measures how small they are exactly. So when you're interpreting, they're going to ask you to interpret this more often than to calculate it. Interpreting, you could use what I said up there about the typical prediction error. You could say predictions made by this model or line are off by whatever it is on average. It's kind of like an average of the residuals, but not quite. All right, and then the second one, I'm going to put stars by these so they stand out from that. The second one that we need to learn how to work with is called the coefficient, it has a fancy name, coefficient of determination. And that's not talking about the psychological determination. I'm so determined to do this, but determination as in determining how well this line fits. So that's what it's talking about. We've got the standard deviation of residuals, and we have the coefficient of determination, which is one more measure of strength or fit. So the coefficient of determination is a fancy name for R squared. Let's think about that for a minute. What is R squared? I'm going to give you a partial proof, but not exactly complete. So let's draw one more scatter plot. I'm sticking with a positive trend. Draw me a line. Let's pick a point that is a little bit above the line, like that one right there. And remember, we have X and Y without the hatch, and then we have X and Y with the hatch. And then there's another one that is where the Y bar is. So this point right here is X comma Y bar. So now there's 3 different Y values depending on what you know. So we have the actual data value. And if I didn't know anything else about this data value, if I didn't know what X is, then actually my best guess for Y would be Y bar. If I don't know X, then Y bar, the average Y, is my best prediction. So that's my prediction that I would use if I didn't have the X. If I have X, and X happens to be above X bar, which is right here, X happens to be over here, and that means I know it's a positive trend, and I know that X is above average, so therefore I would predict Y to be above average. That's my best prediction based on X. But then there's a little bit more that's just a random error that's in the residuals. So what I have is I have this piece right here between the Y hat and the Y bar is the explained variation. Or specific, if we're talking about just one point, it's the deviation, but if you take all of them and put them together, that's the variation. The explained variation is, why is it off the mean? It's off the mean because X is above average, so therefore Y must be above average. And then these ones, X is below average, so Y must be below average. That's the explained, it's explained by the line. So that's that part. And then this piece up here, that's the residual, is the piece that's unexplained variation. It's just randomness that is not explained by the line. So what we want with the line of fit is we want that unexplained variation to be as small as possible, and we want to explain most of the variation by using our line of fit. So basically, if you take all of this put together, if you add them together, you get the total deviation. So let's see, where can I draw that? I'll do that down here. If you add them together, you get the total variation, which is the variation above and below the mean for all the points. And what we're talking about here is how much of that total variation is explained by the line and how much isn't. And so R squared, which is the coefficient of determination, I'm going to shorten this explanation a little bit because I feel like I'm talking too much about something hard, but I'm going to summarize what I'm thinking in my mind by saying R squared is the percent of the variation in the Y values that is explained by the line. That is really an important idea. And there's a lot more that we could do with that. I could tell you what this is called and what this is called and write a whole formula. I'm not going to go there because it's messy, but I'm going to just tell you that if you calculate all of these squares, remember the squares that we're trying to minimize, and you compare them to the squares of the difference between that and the mean, that's where you get this explained and unexplained and total variation. And I'm not going to worry about the formula so much. The important thing is, can you interpret using this sentence? So let's do an example of an interpretation of this. So let's say we have a whole new example. We have dogs' weights versus dogs' heights. And we do our analysis and we get our correlation, which comes out to be 0.8. So in other words, it's not perfectly straight line. It's a strong positive correlation. Heavier dogs tend to be taller, taller dogs tend to be heavier, and so forth. We could use that to find R squared, which is 0.8 squared, which is 0.64. Yes, 8 squared is 64. So if you didn't do that in your head, it's okay. But what this 0.64 tells us is that 64% of the variation, actually I should decide which one's X and which one's Y before I go on. So let's say this is X and this is Y. So the variation in weights we're trying to predict based on the height. So 64% of that variation in dogs' weights can be explained by a linear relationship with their height. So what you do is you plug in your Y value and you plug in your X value over here. And that's what the interpretation of R squared looks like. It's always the percent of the variation in Y that can be explained by the line of fit or by the linear relationship with X. I should probably put that. So you'll notice in your homework, a lot of your homework is interpreting residual plots. Like, look at the residual plot, tell me if there's a pattern or not. Hopefully you would notice if there's a pattern. Interpreting standard deviation of the residuals. They'll give you S most of the time. You won't have to use the formula, but they'll ask you to tell what it means. Predictions made by this line are off by this much. And then interpreting R squared. And this little picture is just trying to help you understand why this interpretation makes sense. But one thing you might do in this class is you're perfectly welcome to just memorize this sentence and be able to plug in stuff into that sentence. So there's nothing wrong with doing it that way. And you're more likely to get it right that way. All right, so that is it for the 3-2C notes. Remember, there's another video you could watch about the proof of why this all works, and it will include the R squared thing in that proof. So watch it if you're interested in the proof.